This lesson is about the inverse trigonometric functions. The purpose of the inverse trigonometric functions is to take a ratio of two sides of a triangle and find out which angle measure would result in that ratio. For instance, we know that the sine of pi over 4 equals the square root of 2 over 2. That's something we've worked with in this class multiple times. So that means that the arcsine, which is the inverse of sine, of square root of 2 over 2 is equal to pi over 4. So for instance, if I was trying to evaluate an arcsine, and I had a right triangle, and this is my observed angle measure, and I know that the sine of that angle measure is the square root of 2 over 2. So that means the opposite side over the hypotenuse is in that ratio. Well then, if I solve for the remaining side, I'd find this side would be the square root of 2, and you can use the Pythagorean theorem to prove that, but that's going to be the case. And if you notice, all of these, if you divide by 2, this would equal 1. So I'm in the ratio of sides, 1 square root of 2 over 2, square root of 2 over 2, which is the ratio of sides for a 45, 45, 90 triangle. So that means this angle measure is 45 degrees, or pi over 4. So that's the idea of the arc functions, which is the inverse trig functions. And sometimes instead of writing arcsine of x, we write sine to the negative 1 of x. And that means the same thing as an arcsine of x. And some students at first initially think of this as being like, I'll write it in red because it's not correct. Think of this as being sine to the negative 1 as 1 over sine x. But that's not the case, because that would technically be cosecant, and the arcsine is not the same thing as cosecant. So it's kind of an unfortunate way that the expression of this type of function meshes with other mathematics. So if you see arcsine, arccosine, arctangent, sine to the negative 1, cotangent to the negative 1, any of your functions written this way, we're talking about an inverse trig function. Before we dive into those, however, let's talk about inverse functions in general, because they're usually not something that are completely understood by this point. So the inverse of an algebraic function is found by swapping your x and y values and resolving for the equation y, or resolving the equation for y. So for instance, a very simple example is a linear equation. So if I have f of x equals 3x minus 5, and I want to find f inverse of x, well, this means y equals 3x minus 5, and then I swap my x and y. So that gives me x equals 3y minus 5. And then next I resolve for y. And in doing that, I get, say, x plus 5 equals 3y, or y equals x over 3 plus 5 thirds. So I can say my inverse function is x over 3 plus 5 thirds. Now, that works great for algebraic functions. Algebraic functions are ones that can be written in terms of x and y such that they are multiplied, added, exponents, divided, all the basic operations. Your trig functions are not algebraic functions, and so we can't do that sort of thing for trig functions. But that's okay, we have a means to work with. But swapping the x and y values essentially swaps the domain and range of the function. And this happens in algebraic functions and in non-algebraic functions. But graphically, this means that a function and its inverse are symmetric about the line y equals x. And as long as a function is one-to-one, it will possess an inverse function. So let me take you to an applet to kind of help explain what's happening with these inverse functions. So in this applet, I have graphed the line y equals x. And I graphed it as a dashed line because it's not actually part of any of the graphs that I'm going to show you. It's just simply there to illustrate the symmetry in the graphs that exist. And the symmetry between the graphs of a function and its inverse is about the line y equals x. So the first thing I'm going to do is show you a linear function. So I have the graph of y equals 4/3 x minus 4. Now, a graph possesses, well, a graph is called a function if it passes what's called the vertical line test. And the vertical line test means that if you can draw a vertical line at any point along the graph, and it only touches one point, or at most one point, then the graph is referred to as a function. But if it crosses two or more points, it's not a function. Another thing to know is that a graph is called one-to-one if it passes a similar test called the horizontal line test. So the horizontal line test, you just do the same thing except with horizontal lines. So if you can draw a horizontal line at any point on the graph, and it only touches the graph at most one place, it passes a horizontal line test. So a linear function certainly does that. Now, when it passes the horizontal line test, that means that a function's inverse exists. And we can solve for that function's inverse since we know the equation. But if all we ever knew was the graph, then what we could do is take every single point that's on the graph and swap it and swap the x and y values and see where the point exists on the other side. So for instance, let me find a decent point here. All right, so this particular point is at 0.66 and negative 2.12. If I look at the image of that point on the other side, it's at negative 3.12 and 0.66, which means that the new point is found just by swapping the x and y values, which is where the symmetry about the line y equals x comes from. So if I map all of the points along the line across this line, this is what I come up with. Certainly I could solve for this inverse function. So if I took the function y equals 4/3 x minus 4, and I swapped my x and y values, then resolved for y, so I would have x plus 4 equals 4/3 y. If I multiply everything through by 3, that would be 3x plus 12 equals 4y, and then divide everything through by 4. I have 3/4 x plus 3 equals y. And if you look at this graph over here, the y-intercept is approximately at 3. And then the next point on my graph, if I go from this particular point, if I go up 3, 1, 2, 3, and then over 4, so this would be about 1, 2, 3, 4, that gives me the next point on the line right here. And if I continue doing that, I would map out all the points on the line. So all of this works. It just shows us that defining an inverse is found by swapping x and y values, which gives us this y-axis symmetry. All right, let's move on to the next function. So let me erase what I have here. y equals x cubed. If I map all the points from y equals x cubed across the line y equals x, I get a function that looks something like this right here. Now, I'm not going to draw the whole thing, go into positive or negative infinity, but you should recognize this graph as the graph of the cube root of x. So the cube root of x is the inverse of x cubed. Okay, if I chose a non-algebraic function, so e to the x, if I swap my x and y values for each point there, then what ends up happening is I get this type of curve down here, which you should recognize as your logarithmic graph. So inverse of an exponential function is a logarithmic function. Let's move on to x squared. Now, only thing different in this function from ones we looked at so far is this particular function does not pass the vertical line test. It fails at almost every single point on the graph, so it's not one-to-one. And in order to have an inverse function, it has to be one-to-one. So let me show you what that means. So I'll draw some of the points on the inverse of this graph, which means to just swap your x and y values. So the newly created graph exists, but it's not a function because it doesn't pass the vertical line test. So we're not saying a graph doesn't have an inverse. We're saying it doesn't have an inverse function, which means that the result is not one-to-one. So the problem there is when you're solving equations, you could have multiple solutions to the exact same problem, and you'd have to make sure you watch out for every single possibility. To simplify things, what we can do is take advantage of what's called the y-axis symmetry of this function. So if you'll notice, the function x squared is symmetric about the line y equals x. Because of that, we can make a domain restriction on this function from 0 to positive infinity as such. And all of the solutions that we would have come up with for the right-hand side of this function are just mirror images of points that exist on the left-hand side of this function. And so it's perfectly fine to use this to define the inverse function, which would look like that. And you may recognize this as the graph of y equals the square root of x. So you have now a function because it's going to pass the vertical line test. And if you'll notice, the restriction that we put on x squared makes it pass the horizontal line test, meaning now that it's one-to-one. So that gives you a brief introduction to what's happening with inverses in general. So now let's look at inverse trigonometric functions. So trig functions are particularly interesting when it comes to inverses. None of the trig functions are one-to-one, but they all have the correct symmetry in order to define an inverse on a restricted interval. So let's take a look at an applet that helps us understand what's happening with the inverse trig functions. All right, so in this particular applet, I'm going to start off by graphing the line y equals x. And I'm going to begin with the function sine. Now, certainly this graph of sine does not pass the vertical line test. Because if I draw a vertical line, I hit a whole lot of points here. In fact, because sine's domain is from negative infinity to positive infinity, I actually hit an infinite number of points. So it is definitely not one-to-one. However, if I were to attempt to draw an inverse, then what I would find is basically that the attempt to draw the inverse would result in a graph that is not a function, because every single point that I could draw a vertical line, this would fail the vertical line test. So we need to put a restriction. All right, let me remove this part. And now I'm going to restrict sine to the interval from negative pi over 2 to positive pi over 2. If you'll notice, every single interval from, say, here to here, or from here over to here, or from here over to here, these are just replicas of this mapping of points. Okay? So it's not y-axis symmetric, but it is does possess what's called origin symmetry, which is another type of symmetry that we can work with in terms of defining a domain restriction in order to come up with an inverse function. And if I restrict my domain to this interval, then the graph of the sine function, the arc sine function, would basically look like this. So it doesn't look like a whole lot. It's just these red set of points here. This lower value down here is negative pi over 2. And if you approximate pi over 2, it's like 1.57. And that's about where I'm at. And then this upper value here is pi over 2, which of course is approximately 1.57. So the range of the sine function is restricted to that interval. And that's a good thing to understand. And basically, if you think of it in terms of angle measures, these would be angles in quadrant 4, and these would be angle measures in quadrant 1. So all of the angle measures that you get out from the arcsine function will be between somewhere in quadrant 1 or quadrant 4. And it's all about the symmetry and making it a function that can define an inverse function. All right, so cosine is similar. You know, the shape of cosine is basically the same as the shape of sine, but it possesses a different type of symmetry. It possesses y-axis symmetry. And the y-axis symmetry is another one that we can define an interval so that we can map, we can come up with a restriction for cosine that would map all the different points that are required in order to define the arc cosine function. So if you'll notice, you know, going from 0 to pi, this mapping right here looks identical, though it's just reflected from pi to 2 pi over pi to 2 pi. You know, and it's the exact same mapping from pi 2 pi to 3 pi. So you just basically have this particular shape over and over again, and that makes the graph of cosine. So we can use that restriction from 0 to pi in order to define the arc cosine graph. So if I map these points across the line y equals x, then this is the shape of the graph that results. So that's what arc cosine looks like. And if you'll notice, it is restriction. This point up here is approximately, well, it's going to be at pi, and pi is approximately 3.14. So that's about where that point lies. And then this point here is at y equals 0. So this would be about 1.57. So any angle measures that you get out from the arc cosine function will either exist in quadrants 1 or quadrants 2. So that's kind of an important thing to understand as well. Now the other trig functions we'll go through rather quickly here because the concept is basically the same, but I do want you to see the graphs of these. So for tangent, this is what the graph looks like. The restriction is from negative pi over 2 to pi over 2. And if I do my mapping of all the points on that interval, yeah, I get a graph that looks like this. And this would be the graph of my arctangent function. And it actually extends from negative infinity to positive infinity, but you know, the highest point I can get for this particular value, it's just, you know, close to 5 pi over 2, but I can certainly go all the way up to positive infinity. For cosecant, this is the graph. It has origin symmetry, so I can restrict my interval to that. And when I draw the graph of the arccosecant, it looks something like this. So this red image. Notice it's not defined at 0. And that's just a property of, you know, where the cosecant function is undefined in the first place. For secant, we have a similar relationship, although the symmetry here is back to y-axis symmetry. So I can restrict to 0 to pi. And when I map all the points for secant, then this is what I come up with. This looking graph right here. For cotangent, of course it's similar to tangent, just a different restriction. And that's what it looks like here. Basically just like tangent, but notice how the arccotangent is entirely positive. It's above the x-axis at every single point. So that's a lot of information to throw at you about these inverse functions all at once. To give you a summary of what you should know here. The individual functions, their restrictions, but most importantly, what quadrants the answers are going to lie in. So for arcsine, the restriction was negative pi over 2 to pi over 2, which was quadrants 1 or 4. So just think of arcsine in terms answers in terms of 1 and 4. Cosine, the restriction was 0 to pi. Its quadrants, the answers for arccosine are going to lie in either quadrants 1 or 2. For arctangent, it's 1 and 4 again. For arccosecant, it's 1 and 4 again. For arcsecant, it is 1 and 2. And for arccotangent, it's also 1 and 2. So I think of these in terms of groups. So when I'm getting answers for these functions, like sine, well, it's arcsine, arccosecant, and arctangent, all grouped together and give answers in quadrants 1 or 4. And then you have cosine, secant, and cotangent, all grouped together to give you answers in either quadrants 1 or 2. Now, with secant and cosecant, there's additional restrictions. You know, cosecant, the y value can't be equal to 0. Secant, the y value can be equal to pi over 2. But essentially, it's still, you know, the same sort of quadrants that we're looking at with sine and cosine. So Sine is related to cosecant because cosecant is just 1 over sine. Tangent is generally related to sine because sine is in the numerator of tangent. Cosine and secant are obviously related. Cotangent's in this group because it's generally, the numerator where the cosine is. So think of them in terms of groups, and that makes it a little bit easier to remember. Okay, let's do some examples. Use the unit circle to solve for the following exactly. Answer using radians. So part A, we want to find the arcsine of the square root of 3 over 2. Now for the arcsine, what we have to keep in mind is that the arcsine is going to be restricted to the quadrants 1 or 4. Since we're doing the arcsine of a positive value, that means in this case I'm going to be using quadrant 1. So I need to figure out where the sine is equal to 3/2, or equal to the root 3 over 2. And the sine in the unit circle is the y value. So it looks like I am right here, and that is the angle measure pi over 3. And the expectation is that if you're doing a lot of these, that you'll take the time to write out a unit circle in order to answer these questions a lot faster if you've got a bunch of them. If you just have a couple, it might not be worthwhile to draw an entire unit circle to answer them, but certainly if you have a lot, it would be a very good thing to do. B, the arccosine of 0. So the cosine is the x-coordinate, and cosine, we just have to remember we're going to answer in quadrants 1 or quadrant 2. And since this is positive, that's going to put us in quadrant 1. So we're technically it's going to be a quadrantal angle, but it doesn't make a lot of difference because this is the only value in the range from 0 to pi effectively, where cosine is 0. That's the x-coordinate. So the answer here is pi over 2. For C, I want to find the arctangent of 1, and I'm just going to pull my unit circle down here so I can still see it. So the arctangent of -1. So arctangent, also like sine, the answers are going to either be in quadrant 1 or quadrant 4. But the thing you have to be careful of when you're answering with the quadrant 4 is the restrictions are always negative to pi over 2 to positive pi over 2. So instead of answering 3 pi over 2, if this happened to be my value, I need to answer negative pi over 2. And similarly, 7 pi over 4 would be the same thing as negative pi over 4. This is going to be negative pi over 6. And this one would be negative pi over 3. It just comes down to the range of the arc trig functions being from negative pi over 2 to positive pi over 2 for sine, tangent, and cosecant. So in this case, I want the arctangent of -1 and the arctangent of -1. What we're going to do there is you have to kind of notice that since tangent is defined as sine theta over cosine theta, what we need to occur is basically these two values to be equal to one another in order for them to divide to 1. And in particular, the only times where these things are equal is when we have root 2 over 2 for sine and cosine. But also, since this value is going to be negative, I'm going to need one of these to be negative. And it doesn't technically matter which one, but there's only going to be one that has root 2 over 2 as your x and negative root 2 over 2 for your y. The angle measure that that is associated with is negative pi over 4. So negative pi over 4. And when it comes to doing trig functions other than sine or cosine, you kind of have to do arguments like this because we don't necessarily have spelled out the y divided by x, for each of the different points. We have to kind of do that in our head. D, we want the arc cosecant of negative 2. Now, arc cosecant of negative 2, let me make some changes here first, because cosecant's a little bit more difficult to work with than, say, sine. So let me write this first as arc cosecant of negative 2 is equal to some value. Now just call it x. I'm not meaning an x coordinate or a y coordinate or anything like that, just a value that I don't know. Now, what that means is if I took the cosecant of both sides, then I could say negative 2 is equal to the cosecant of x, which also means negative 2 is equal to 1 over the sine of x. So I think you might be able to see what I'm doing here. I'm just trying to rewrite this so that I'm looking for a value of sine rather than a value of cosecant. If you're comfortable with cosecant and secant values, you don't need to do this, but for those that are uncomfortable with cosecant and secant, you can always change it into sine or cosine regardless. So I'm going to basically flip both sides of this, which means I have negative 1/2 equals sine of the angle measure that I'm interested in. So remember, cosecant is either going to be in 1 or 4. And in this case, we're going to be in 4 because the sine has to be negative. So I just need to look to where my sine is negative 1/2. That's right there. And the angle measure that I'm interested in is negative pi over 6. Use right triangle trigonometry to solve the following exactly. Answer using radian measure. So let's say you didn't have a unit circle handy and you wanted to solve one of these. Or you just had one problem to solve and you didn't want to go through the process of drawing out an entire unit circle to answer it. And I completely understand that. There are still ways of answering this problem. So in order to do that, let's think about just, a right triangle. So cotangent is going to be, the answers for arc cotangents are going to be in either 1 or 2. And because this is negative, it is going to be in quadrant 2. So I'm going to draw a reference triangle in quadrant 2. Now, what I know about this is that if the arc cotangent, let me draw it over here. So if the arc cotangent of negative root 3 over 3 is equal to some angle measure, then if I take the cotangent of both sides, oops, wrong parentheses there. If I take So I'm just taking the cotangent of both sides. The cotangent and the arc cotangent are inverses of one another. So it's like multiplying and then dividing. They cancel each other out. So that means the same thing as the cotangent of theta equaling negative root 3 over 3. So this angle measure that I've defined, its cotangent is negative root 3 over 3. Another way I can think of this is, so cotangent is the inverse of tangent. And tangent is the opposite over the adjacent side. Remember SOHCAHTOA? So this is the adjacent side of the triangle over the opposite side. So the adjacent side of this triangle is going to be negative root 3. The opposite side is going to be root 3. And I've chosen the negative on the x-axis just because I'm in quadrant 2 and that's the way quadrant 2 is set up. So then I would need to figure out what the radius is up here, and get to find that through the Pythagorean theorem. So if I take negative root 3 squared plus 3 squared equals r squared, this would be 3 plus 9 equals r squared, 12 equals r squared. So r equals the plus or minus square root of 12, which the square root of 12 can be factored down to, the square root of 4 times 3, or 2 root 3. And because r is always positive in trigonometry, this is going to just be 2 root 3. Now, if I divide everything through by the square root of 3, then I end up with negative 1 here, root 3 here, and 2 here. So I'm in the ratio of sides of 1, root 3, 2. So this is the ratio of sides of a 30, 60, 90 triangle. And root 3 is slightly larger than 1, so the 60-degree angle measure is across from it. So that means this angle measure here is 60 degrees. Or, since I need to answer in radians, pi over 3. But this is the angle measure that I need to answer with, which would be pi minus pi over 3. So that would be 3 pi over 3 minus pi over 3. So the 3 pi over 3 is just equal to pi. So I'm just getting a common denominator. So 2 pi over 3. So in this next example, I'm going to show you, because I want you to know how to do the secant function as well. But I'm going to use the unit circle because, like I said, it's just a whole lot easier. All right, so secant's answers are either going to be in 1 or 2. I'm going to change this into arc cosine because that's just easier. So I just need to invert this fraction. So then 3 divided by the square root of 3 is the square root of 3. So it's root 3 over 2. And cosine is root 3 over 2. That's my x value at pi over 6. A whole lot easier. That's kind of arguable. That's not really arguable. Next, use the calculator to find the value of the following. Answer in radians. Okay, so the calculator can find these arc functions as well. And if you'll notice, above the sine button, you have sine to the negative 1. Above cosine is cosine to the negative 1. And above tangent is tangent to the negative 1. So you have these arc functions as well. And if you're answering in radians, just make sure you're in radian mode. So we would just do second and sine and to get the arc sine function, 0.5413. And we get 0.5720. And just round the number of decimals that are appropriate for your problem. You'll generally be asked the number. For cosecant, again, there's no button here for cosecant. There's only, arcsine, arccosine, and arctangent. We can evaluate arccosecant by doing the arcsine of 1 over the angle measure provided, or the number provided, which is a ratio of sides. So I would do, in this case, arcsine of 1 divided by negative 1.255. And notice I used the negative here instead of the minus. The calculator does distinguish between the negative and the minus. If you use the wrong one in the wrong place, it will give you the wrong answer. So again, I'll just round to 4 decimals here. So negative 0.9220. Arccotangent of 30.5119. So this would be the arctangent of 1 over that. And 1 divided by 30.5119. And that comes out to 0.328. 0.328, I think it was. Yes. All right. So that's how you work with your calculator. As we get into applications problems later on in the class, you'll see this more and more. Next up, evaluate the expression tangent of arccosine of 5/13 without using a calculator. So if you could use a calculator, you could approximate the value. You could just take the arccosine of 5/13, plug that answer into tangent. Now, in order to do this without a calculator, we have to use right triangle trigonometry. So to do this, one thing we have to recognize is the input of the tangent function is some angle measure theta. Okay? So the arccosine of 5/13 is equal to that angle measure theta. Or if I take the cosine of both sides, that means 5/13 is equal to the cosine of theta. So cosine is defined as the adjacent side over the hypotenuse. So just remember, so katoa. So cosine is adjacent over hypotenuse. So I'm just going to draw a right triangle to get me started. And I'm going to call this theta. And what I know about that angle measure theta is that the cosine is 5/13, which is the adjacent side over the hypotenuse. Next, I'm going to solve for this remaining side here, because that's going to tell me well, I'll show you why. So 13 squared is equal to x squared plus 5 squared. So 169 is equal to x squared plus 25. If I subtract 25 from both sides, 144 equals x squared, or x equals, it's either going to be plus or minus 12. But we can safely assume that it is positive 12 because the arccosine function can only give values in quadrants 1 or in quadrants 2. And because the value here, 5/13, is positive, the result is going to be something that's in quadrant 1. So that means that we can safely assume that x is equal to 12 because x is positive in quadrant 1. So then we don't know what angle measure theta is. But since we know all three sides of the triangle around angle measure theta, we can now answer what the tangent of theta is. The tangent of theta is the opposite side over the adjacent side. So the answer here is 12 fifths.